What if I told you that right now, as you watch this video, there are objects in the universe so impossibly bright that a single one outshines an entire galaxy of 200 billion stars? These cosmic lighthouses called quasars are the most luminous phenomena ever discovered, beaming energy across billions of light years of space with such intensity that they can be seen from the edge of the observable universe. But here's the truly mind-bending part. These brilliant beacons are powered by something that supposedly lets nothing escape, not even light itself. Welcome to the paradox of quasars, where the darkest objects in existence create the brightest light shows in the cosmos. Let's travel back to 1963, when astronomers were absolutely baffled by strange radio signals coming from what looked like ordinary stars. But as telescopes improved and our understanding deepened, scientists realized these weren't stars at all. They called these mysterious objects quasi-stellar radio sources, which was quickly shortened to quasars. They were witnessing something far more extraordinary, something that would revolutionize our understanding of the universe itself. These weren't nearby stellar objects, but incredibly distant powerhouses located in the hearts of ancient galaxies, shining from a time when the universe was just a fraction of its current age. So what exactly is a quasar? At its core, a quasar is the incredibly bright center of a distant galaxy, powered by a supermassive black hole actively feeding on surrounding material. Picture this: a black hole with a mass millions or even billions of times that of our sun, sitting at the center of a galaxy, pulling in enormous amounts of gas, dust, and even entire stars. As this material spirals inward toward the black hole, it forms what's called an accretion disk, a swirling maelstrom of matter heated to millions of degrees. The friction and compression in this disk generate temperatures so extreme that the material radiates across the entire electromagnetic spectrum, from radio waves to X-rays, creating a luminosity that can exceed the combined light of every star in the host galaxy by hundreds of times. The physics behind quasar brightness is almost incomprehensible when you really think about it. We're talking about objects that can release the energy equivalent of trillions of suns, all concentrated in a region smaller than our solar system. The accretion process converts mass to energy with incredible efficiency, actually more efficient than nuclear fusion in stars. When matter falls into the gravitational well of a supermassive black hole, it can convert up to 40% of its mass into pure radiant energy. For comparison, the nuclear fusion happening in the core of our sun only converts about 0.7% of mass to energy. This means that black holes, despite being the ultimate cosmic vacuum cleaners, are paradoxically the universe's most powerful energy generators when they're actively feeding. But quasars don't just shine bright, they also shoot powerful jets of material perpendicular to their accretion disks. These relativistic jets, streams of charged particles accelerated to nearly the speed of light by intense magnetic fields, can extend for hundreds of thousands of light years into intergalactic space. When these jets point directly toward Earth, we observe what's called a blazar, an even more intense and variable type of quasar. The particles in these jets are moving so fast that relativistic effects make them appear even brighter and more energetic from our perspective. It's like cosmic spotlights aimed across the universe, and occasionally, one of those spotlights happens to be pointing straight at us. Now here's where quasars become even more fascinating as cosmic time machines. Because light takes time to travel through space, when we observe distant quasars, we're literally looking back in time. The most distant quasars we've discovered are so far away that their light has been traveling for over 13 billion years, meaning we're seeing them as they appeared when the universe was less than 1 billion years old, just a child in cosmic terms. This makes quasars invaluable tools for studying the early universe. They act as backlights, illuminating the gas and structure that existed between them and us, helping astronomers map the evolution of galaxies, the distribution of matter, and the chemical enrichment of the cosmos over billions of years. The discovery that quasars were incredibly distant objects solved one mystery but created another. How could supermassive black holes, objects millions or billions of times more massive than the sun, form so early in the universe's history? This is one of the biggest questions in modern astrophysics. Current theories suggest that the first black holes might have formed from the collapse of massive primordial stars or from direct collapse of gas clouds in the early universe. Once formed, these seed black holes could grow rapidly by consuming surrounding material and merging with other black holes. But even with these accelerated growth mechanisms, creating billion solar mass black holes within the first billion years of cosmic history requires some extreme conditions and processes that we're still working to understand fully. What's equally remarkable is that quasars were much more common in the early universe than they are today. When we look at the distant, ancient universe, quasars are everywhere, but in the nearby modern universe, they're extremely rare. This tells us that quasar activity represents a phase in galaxy evolution. When galaxies were young and gas-rich, their central black holes had plenty of fuel and shone as brilliant quasars. As galaxies aged and used up or expelled their gas through star formation and quasar-driven winds, the fuel supply dwindled, and the quasars essentially turned off. Today, most supermassive black holes, including the one at the center of our own Milky Way galaxy, are relatively quiet, no longer shining as quasars but sitting dormant, waiting for a fresh supply of material to ignite them once again.
The impact quasars have on their host galaxies is profound and something we call feedback. The enormous energy output from a quasar doesn't just radiate harmlessly into space. Much of it interacts with the surrounding galaxy, heating and expelling gas, effectively shutting down star formation. This might sound destructive, and in some ways it is, but this feedback mechanism is actually crucial for galaxy evolution. Without it, galaxies would convert all their gas into stars too quickly, and the universe would look very different from what we observe. Quasars essentially regulate galaxy growth, preventing them from becoming too massive and helping establish the relationship we observe between black hole mass and galaxy properties. It's a cosmic balancing act where the brightest objects in the universe also serve as cosmic thermostats. Studying quasars has also revealed fascinating details about the structure of space-time itself. Because quasars are so bright and so distant, they're perfect targets for observing gravitational lensing, where the gravity of massive objects between us and the quasar bends the quasar's light. Sometimes this creates multiple images of the same quasar, arranged in beautiful patterns called Einstein rings or Einstein crosses. By studying these lens quasars, astronomers can measure the expansion rate of the universe, map the distribution of dark matter, and even detect planets in distant galaxies through the subtle changes they cause in the quasar's light. Quasars have become tools for probing not just their own nature, but the very fabric of the cosmos. As our technology advances, we're discovering new aspects of quasars that continue to surprise us. Modern telescopes can now observe quasars across the entire electromagnetic spectrum, from radio waves detected by arrays like the Very Large Array to X-rays captured by space observatories like Chandra. Each wavelength reveals different aspects of the quasar phenomenon. Radio observations show us those spectacular jets. Optical and ultraviolet light comes from the hot accretion disk, and X-rays reveal the innermost regions near the black hole's event horizon. By combining all these observations, we're building a complete picture of how quasars work and how they've shaped the universe throughout cosmic history. The story of quasars is really a story about extremes. They're extreme in brightness, extreme in energy output, extreme in distance, and extreme in their impact on cosmic evolution. They represent moments of intense activity in the lives of galaxies, phases when supermassive black holes feast on surrounding material and shine with the light of trillions of stars. They're windows into the early universe, allowing us to study conditions that existed over 13 billion years ago, and they're laboratories for testing our understanding of gravity, relativity, plasma physics, and the fundamental forces of nature under the most extreme conditions imaginable. Every quasar we discover adds another piece to the puzzle of how the universe evolved from the simple, smooth state shortly after the Big Bang to the rich, complex cosmos we see today, filled with galaxies, stars, planets, and ultimately, life itself. The brightest objects in the universe are helping us understand the darkness from which everything emerged.